Hi, lectures 36 and 37 represent both the pinnacle and end of our course on differential equations and linear algebra. For my students at Bethel here in fall of 2020, because of COVID, you are going to end here with lectures 36A, 36B, and 36C. For future semesters, there's going to be one more lecture with lecture 37A, 37B, 37C. I am really excited about this content. It's going to represent, in a lot of ways, the culmination of everything that you've learned about calculus, differential equations, linear algebra. Here in lecture 36A, we've got especially very, very pretty pictures. We're going to talk about flows on non-Euclidean phase spaces. What do I mean by that? I mean not the real line, not R2, not R3, but curved surfaces, for example, a cylinder and a sphere. We will review stability in Lyapunov Second Method with examples, both in 1, 2, and 3 dimensions. And at the end, I'm probably not going to have time to go through the details, but it will be there for you in the PowerPoint. More detail about the competing species local Lyapunov function construction that I talked about in lecture 35A. For my students, the main thing here in lecture A is to get the big picture. There are a ton of computational details that you don't have time to check. I want you to believe that you could check them. You want to focus more on the big picture. Probably for the final exam, you'd be tested more on the concepts, true-false questions, multiple choice questions related to this content. So let's go ahead and get into it. What is, first of all, the best phase space for the pendulum model? That sounds like a weird question. What do you mean, best phase space? Well, let's get into some details here. Our pendulum system was a first-order system of differential equations in theta and v, where theta was the angle of the pendulum, theta equals 0 is pointing straight down, theta is positive over this direction, and theta is negative over this direction, and v is the angular velocity. Theta would be in radians, and v would be in, say, radians per second. Here it was. This includes damping when b is positive. If b is 0, then it's an undamped pendulum, and it was a Hamiltonian system that we saw. But in this first picture that I'm going to show you, I'm going to assume b is positive. We're going to see the phase plane for this damped pendulum system. It's periodic in theta, though. Before we see the picture, realize that because that sine term there, sine is a periodic function of period 2 pi. The phase plane itself, its phase portrait over the entire plane, is periodic. Here's a picture of it. Kind of messy. Get your bearings here. The brown line here, which is the theta axis, is where v is 0. That is the theta nucline. Solutions cross that with vertical tangents going down here, down there, up there. The pink sinusoidal type curve is the v nucline, where dv dt equals 0. Set this equal to 0, solve for v as a function of theta. You get a sinusoidal function of theta. That is where dv dt is 0. Solutions cross that horizontally. Where pink and brown intersect, these black dots, those are equilibrium points. You can see that this one, for example, is a spiral sink. That's representing the equilibrium point pointing straight down, where because of damping, you eventually approach the straight down equilibrium point. These two, for example, are saddle points. They represent straight up solutions, which you can never observe in real life. They're not stable. Ever so slight of a perturbation from straight up will result in solutions moving away from those. Some solutions, if you started off with a high enough initial velocity, would keep going around and around and around. You'd keep moving through this phase plane to the right, letting theta to continue to increase even past 2 pi if you keep going around and around with a high enough initial velocity, though because of damping, eventually you'd come down to an equilibrium. You'd eventually come down towards something along the theta axis. There's infinitely many equilibrium points along the theta axis, and yes, this is periodic. You keep going periods 2 pi, you're going to see a repeat picture. Because of this, and because there are only two true physical equilibria, the pointing straight down situation and the pointing straight up, it would be better, technically speaking, if we wrapped the phase plane around to create a phase cylinder as our phase space. Imagine grabbing the plane here, use your imagination, curling it around, gluing the pieces together at, say, theta equals pi and theta equals negative pi, and then getting rid of everything else. You'd have a phase cylinder that would only have two equilibrium points, And those two equilibrium points would represent straight down and straight up. This one being stable, this one being unstable. What would the phase cylinder look like? Some very pretty pictures here. For both the undamped and damped cases, we could do it. So I'm about to show you first the undamped case when B is 0. That was really a Hamiltonian system. Solutions lied on the level curves that you saw in the previous picture, which were really level curves of the Hamiltonian function, and also for the Lyapunov function in the damped case when you take it to be the opposite of the Hamiltonian function for the undamped case. Here it is. There's a phase cylinder in the undamped case. Isn't that pretty? That's the undamped case. These black dots are the two equilibrium points, and they're the only two. This one is at theta equals 0. You want to go around the horn for theta. Theta goes from 0 to 2 pi, and then it repeats essentially. You're at the same spot when you keep going around and around. This one back there is the unstable one at theta equals pi, 180 degrees straight up. You can see solution curves going around this one. That's like a center. It's Lyapunov stable. It's not asymptotically stable. It's Lyapunov stable. This one turns out to be a saddle point. Solutions go away from it. Solutions in blue here in this undamped case represent, because of no damping, a solution that goes around and around counterclockwise forever and ever. You go faster at the bottom and slower at the top. V is higher. The V direction here is going upward. V is higher when theta is close to 0 and lower over here when theta is close to pi. So you go fast at the bottom and slower at the top, but you would keep going around and around forever, like that. Here's the damped picture. And you can see now that this equilibrium point, the straight down, is now a spiral sink. This point back there is still a saddle point. I do have these in Mathematica. This is the damped case right here. And the nice benefit about Mathematica is we can rotate these things around if we like. Enter some code here. So here is the undamped case. The nice thing now, though, is I can rotate this around. I can use my cursor and rotate this around, and I can see that unstable one back here. I didn't draw enough solution curves in there to clearly see that it's a saddle point, but it would be. There would be a separatrix going off this direction around the cylinder, another one coming in from this direction. In fact, it would be the same solution curve that would represent almost being straight up at minus infinity and then going to, or go around this way, to almost being straight up as t goes to plus infinity. You'd also have separatrices down here. In the damped case with friction, we can turn that one around as well and see the other side. Okay? That's the benefit of having the Mathematica, which will be in the course documents in the Google Drive. Very, very nice, pretty pictures. I like it a lot. You get the basic idea? This is a better phase space because it's focusing on the true state of the system and the fact that there really are only true two physical equilibrium points instead of infinitely many. Now let's look at a system on a sphere instead of a cylinder, by first looking at a three-dimensional system that has what are called invariant spheres. This is going to be a three-dimensional system, and if you start with an initial condition on a certain sphere, on any sphere actually, centered at the origin with a certain radius, that solution curve will stay on that sphere. It's not easy to come up with examples like this, and in fact, I'm going to tell you this example and then some other examples here I got from a book that I'm going to recommend to you. It's not our Blanchard, Devaney, and Hull textbook. It's this one, Differential Equations by Selwyn Hollis. I got some cool examples that I'm going to show you in this lecture here. This is one of them. It's clearly not obvious. That's kind of a strange thing to say. It's definitely not obvious that this has invariant spheres. There's no way that I know of that you can just look at that and say, hey, I bet that's got invariant spheres. So what would we do in this kind of situation? Well, you would first look for equilibrium points like usual. And we will do that. But before that, let's focus on the fact that it's got invariant spheres. This is not a Hamiltonian system. Okay? We've looked at Hamiltonian systems where solutions are on the level curves of the Hamiltonian function, and evidently maybe in a higher dimensional Hamiltonian system, the solutions would be on level surfaces of a Hamiltonian function? Well, it turns out you can't have a Hamiltonian system if it's three-dimensional. Hamiltonian systems only exist for even-dimensional system, two-dimensional, four-dimensional, six-dimensional, etc. However, this system does have a conserved quantity, kind of like a Hamiltonian function, but the system itself doesn't have the right form to truly be a Hamiltonian system. This function right there, x squared plus y squared plus z squared, whose level surfaces are spheres centered at the origin, is a conserved quantity. If you differentiate it along solution curves, you get 0. Here are the details. Along any solution curve, we've seen this before. Take the derivative along a solution curve, use the multivariable calculus chain rule, plug in the right-hand side functions here, here, and here from the system in place of dx dt, dy dt, dz dt. Also take the partial derivatives of L with respect to x, y, and z. And amazingly, almost as if by magic, everything ends up canceling. This cancels with this. This cancels with this. These two things here and here cancel with this. They all cancel. And finally, oops, I made a mistake. This cancels with that. This cancels with that. Everything cancels to 0, no matter what point you're at, and so therefore also no matter what t is. There's a t in the background in these calculations. I'm not explicitly putting it in there because I don't know the formulas for x, t, y of t, and z of t. That's why. It's a nonlinear system. It's impossible to find actual formulas for these functions, but you can still do this calculation and see that you always get 0. No matter what point you're at, no matter what t is. So therefore, this function is conserved. It stays constant along solution curves, but its level surfaces where it equals a constant are spheres centered at the origin. Now let's try to find the equilibrium points, like I was mentioning a couple minutes ago. Set all these things equal to 0, solve for x, y, and z. Typically what happens in this kind of situation is each of these equations is going to represent some surface, some two-dimensional surface in three-dimensional space. And typically, if you've got 3 of them, they will intersect each other at discrete points. That does not happen here. Interestingly, instead, you get a curve of equilibrium. A curve of equilibrium points, every point along the curve being an equilibrium point. How could you verify that? You could, for example, solve the third equation for y as a function of x. Look at that equation. Subtract x from both sides and factor out a y from the left side to get that. Now solve for y as a function of x by dividing both sides by -1 minus x. Canceling the negative signs gives you y equals x over x plus 1 as long as x is not -1. That's where this quantity equals 0. That equation defines a surface in three-dimensional space where h is always 0, where dz dt is always 0. Now solve the second equation, this one, for z as a function of x. Add x squared to both sides, factor out a z on that term to get this, divide both sides by 1 plus 3x. Z is x squared over 3x plus 1 as long as x is not equal to -1/3. Amazingly, and this is the thing that would be difficult to come up with on your own, if you plug both of these expressions into the first equation in place of y and z, you get a true equation no matter what x is. That is unusual. They both turn out to be consistent with the first equation. Go to that first equation, go to its left-hand side, replace y with x over x plus 1 and multiply by x to get this. Replace y with x over x plus 1 there as well, and replace z with x squared over 3x plus 1 here and here. Take the time to check. You're going to get this and this. If you get a common denominator of x plus 1 times 3x plus 1, everything cancels. These two things cancel, and these all cancel with each other to give you identically 0. It's consistent with the first equation. So that is what means you really have infinitely many solutions. X can be anything except -1 or -1/3, and once y and z have been defined this way, in a sense x is a free variable, then you will get a point that solves the system, and therefore will be an equilibrium point of the system, of the differential equations. And it will have to be a curve. It's a parametric curve. Every point, which means infinitely many points, on the following parametric curve is an equilibrium point. It's a parametric curve where x is the parameter, not t. There's no t's here. As you let x vary from minus infinity to infinity, don't let it equal -1, don't let it equal -1/3, you will get a curve. Evidently, we'll get a curve in three pieces because we've got these two things that x cannot equal. So we got invariant spheres, and we got a curve of equilibria that might intersect the unit spheres, or the various spheres. We're going to look at the unit sphere here of radius 1. Yeah, let's do that. Let's look at the unit sphere of radius 1. This point is on the unit sphere when its distance to the origin is 1. Think about the distance formula in 3 dimensions. That would be the square root of this squared plus this squared plus this squared. Since I'm setting equal to 1, I can actually get rid of the square roots. I'm going to show you Mathematica here to do this. And say this squared plus this squared plus this squared without a square root equals 1. Solve for x, you'll get 2 solutions. X is about -0.298552 and x is about 0.861861. For some radii, different spheres, we will see you actually get more than 2 solutions. You could get 4 solutions sometimes. You might wonder, could you get 0 or 1 solution? That actually can't happen unless you're at the origin, which is really not a sphere. It's a sphere of radius 0, but that's not really a sphere. The origin is an equilibrium point, by the way. The resulting points, if you plug in those values of x, are these 2 points. Plug in these 2 values of x, here and here, there and there. I rounded more. Find y and z using these expressions for those values of x. These are 3 points that are approximately, not exactly, but approximately on the unit sphere. The flow is quite beautiful. There it is. Whoa. Oh, I just love that. Isn't that beautiful? What are the directions here and what's going on? This black axis going this way is the positive x-axis. X is going from -1 to 1 here. This one going that way is the positive y-axis. Y goes from -1 to 1. And upwards, like this, that's the positive z-axis. Z going from -1 to 1. The red, blue, and green curves that you see are solutions. You can see they're staying on the unit sphere. The black dots are your 2 equilibrium points. What's this orange curve in there? That might look like it's not on the sphere, perhaps. Yeah, it sticks out. That's the curve, well, one of the curve of equilibria. There's another piece of the curve of equilibria. Let's see this on Mathematica as well and see that we can rotate it. Example with invariant spheres. You can get Mathematica to solve for y and z in terms of x, like I did. I can define a curve of equilibrium points. I can solve for where the distance to the origin is 1, and I get approximately the numbers that I showed you. I can plug those numbers into the curve of equilibria and get approximations for the points that I'm after. And I can use ND-solve to find solutions. And now once I've got this picture, I can rotate this. And yeah, I don't know what that plane was there. I don't know why that shows up there. Probably some numerical error. I see that this sphere is not intersecting this other piece of the curve of equilibria. But if I made the radius bigger, it would. Bifurcations would occur on the sphere. This would be an interesting REU, undergraduate research project too, I think. Let the sphere increase and describe the bifurcation that happens. But here we've got 2 equilibrium points on the sphere. They're both spiraling. Evidently, one must be a spiral source and one must be a spiral sink. If I let time be animated, which I do here, then we can see which one's the spiral source and which one's the spiral sink. I'm letting t increase from 0. And I'm seeing solutions that are moving away from this one, it seems, and going toward that one. You might wonder what kind of calculus could you do on the sphere that could perhaps verify that's a spiral sink and that one's a spiral source. You need differential geometry, you might say, to help you understand what kind of calculus you might need to verify that. That could be a research project as well. But here, we're just content to enjoy the picture pretty much and get the basic idea, conceptual idea that for my students, again, you might have true-false questions or multiple choice questions about for the most part. All right, now a few more topics for this lecture A. Let's start by reviewing stability and Lyapunov functions and Lyapunov's second method. Then we're going to look at relatively simple examples in 1, 2, and 3 dimensions of Lyapunov's second method for stability. Then I've got some slides again that correspond to lecture 35A, where I constructed a local Lyapunov function for a competing species model. I'm not going to talk about that content, but I will show it to you quick, and you can download the slides to see it and check the details. And by the way, I'm sure I probably made a mistake somewhere, or at least one mistake somewhere, so let me know if you see a mistake. We got this theorem about stability, essentially saying that if all the eigenvalues of a Jacobian matrix evaluated at an equilibrium point have negative real part, then the equilibrium point will be asymptotically stable. It will be some sort of sink, possibly with a mixture of spiraling and non-spiraling. We are talking about a nonlinear system here, okay? It's essentially the Jacobian method for linearization. We are talking about hyperbolic equilibrium points because the real part of all the eigenvalues is negative, which would imply hyperbolicity, but I sort of added that at the beginning here. This, I have found, is sometimes called Lyapunov's first method, though that's not consistent when you look online. There are other things that are called Lyapunov's first method, but this is essentially a linearization to prove stability, asymptotic stability, in fact, when all the real parts of all the eigenvalues are negative. I'm not going to talk about structurally stable here. Let's move on to Lyapunov's second method, which we want to illustrate with some examples here. This is a rough statement. It's not a precise statement. It's not really a theorem as stated, okay, because it's not precise enough. I'll point out where it's not precise. Let y(q) be a hyperbolic equilibrium point of this nonlinear system, where f is a nice function, essentially is what that means, on some domain, capital omega. Then, if there exists, I'm assuming, if there exists a local Lyapunov function, L of y, defined near this point, that's a vague word. That's part of why this is not a theorem as stated. What does near mean? If there's a Lyapunov function in the sense that derivatives along solution curves are always less than or equal to 0, and also L achieves a minimum at the equilibrium point, then the equilibrium point is stable, Lyapunov stable. It might be a sink, it might be some sort of center in higher dimensions. Furthermore, if the derivative of the Lyapunov function along non-equilibrium solutions near the equilibrium point is strictly negative, strictly less than 0, when you're not at the equilibrium point, then you can even say it's asymptotically stable. Solutions approach the point. It's a sink. That condition about being strictly negative can be relaxed a little bit, kind of like in our Blanchard-Devaney Hall book. If it's equal to 0 at a discrete set of points, it's still going to be asymptotically stable. And there's going to be an example I'm about to show you here soon where that technically happens. Okay? Technically speaking, you should always use this try this theorem first. And if it doesn't work because perhaps some of the eigenvalues have 0 real part because they're purely imaginary, but you still suspect the equilibrium point is a sink, then you can rely on Lyapunov's second method, perhaps. Well, there's a big if. How do you construct the Lyapunov function? That can be very difficult in general. The examples we're looking at here, it's relatively easy. Here's a one-dimensional example. Using linearization, in other words, Jacobian matrices, is usually good enough to determine stability of an equilibrium point, like I just mentioned, because most equilibrium points are hyperbolic. Okay, you come up with some system of random equations, and any equilibrium points are likely to be hyperbolic. Lyapunov's second method becomes necessary in the unlikely case when we suspect that a non-hyperbolic equilibrium point is either Lyapunov stable or asymptotically stable. Maybe we suspect it because that's just the way it looks in the experiments or the solutions that we're seeing and we are approximating. This is easiest to see for one-dimensional examples, like this one. dy dt is negative y cubed. Going back to chapter 1 here, that's an autonomous first order scalar equation. You can make a phase line for it. It's got one equilibrium point at y equals 0. If you graph the right-hand side function, f of y as a function of y, its graph looks like this. Negative y cubed. It does change sign from positive to negative as y increases through 0. When y is less than 0, solutions are increasing because the value of this function is positive. When that's when y is negative. When y is positive, solutions are decreasing because the value of this function is negative. This point at y equals 0 is a sink. We can see that qualitatively. However, the linearization theorem from chapter 1, which is really a one-dimensional Hartman-Grobman theorem, does not apply. It tells you no information because the derivative of this function at 0 is 0. The tangent line there is horizontal. So the derivative linearization is not telling you whether it crossed the axis or not. You have to just know based on the graph. However, it does have a Lyapunov function that is strictly negative in its derivative along solution curves, and therefore y equals 0 technically is an asymptotically stable equilibrium point, though when you get real close to 0, these solutions move very slowly. In fact, all sufficiently nice autonomous first order ODEs, one-dimensional ODEs, are gradient systems actually, with potential function equal to the integral of the right-hand side function. And you can take the plus c to be 0. So v of y is a gradient function, a potential function I should say, of this equation here. It's the integral of the right-hand side. And as I've said before, that must mean its negation, negative v, should be a Lyapunov function. And also again note that y equals 0 is the only equilibrium point. How do you verify that? Use the one-dimensional chain rule instead of a multivariable calculus chain rule. Differentiate this along a solution curve. ddt of L of y of t is L prime of y times dy dt, where this does depend on t as well, but I'm pretending I don't know the formula for the solution here, so I'm not plugging in that function. L prime, though, is, here's L, no negative sign there, its derivative is positive y cubed. That's where this y cubed comes from. But dy dt, because of the differential equation, is negative y cubed. So you get negative y to the 6th, which is strictly negative when y is non-zero. This is a Lyapunov function. The origin in this one-dimensional case is asymptotically stable by Lyapunov Second Method. Actually, it is possible to find y of t here. You can separate variables. And it turns out if the initial condition is positive, then y of t equals this. You can double check that. And this function is a function of t simplifies to this. And if you graph this for any positive y0, you'll see it's a decreasing function. Its derivative is negative. Okay? That's just an aside. You don't need to do that. Here's a two-dimensional example. What about a reasonably simple two-dimensional example where we need a Lyapunov function? We can go back to the example from lecture 33a, where we had a non-hyperbolic equilibrium point at the origin. In 33a, I added an extra factor of mu in here as the coefficient of xr squared and yr squared there, where r squared is x squared plus y squared, the square of the polar coordinate, that is the distance to the origin. I'm taking mu to be -1. That does make the origin a sink, but it's not hyperbolic. You can't use that first theorem here. But there is a Lyapunov function. In fact, it's x squared plus y squared. Here are the details that verify this is strictly negative when r is positive. Okay, when you're not at the origin. Take the time to check that. These details aren't too hard. Very soon the details get a lot harder. What about a three-dimensional example? Dare we try? Here's another example I got from the other book that I showed you. Yikes, signs involved. Does this have any equilibrium points? It turns out the origin is an equilibrium point. X is 0, y is 0, z is 0 makes this all 0. If you try linearizing near the origin, you'll see it's not hyperbolic. I didn't take the time to check that. But it does turn out that this function is a local Lyapunov function. That's not obvious. But if you check it by differentiating along the solution curve, you do get a quantity that is definitely always less than or equal to 0 when the z is close to 0. And it turns out to be strictly less than 0 along solution curves, except for discrete sets of points. So it turns out by a relaxed version of the second method that the origin will be stable here. Note this kind of set, it turns out with this example, will serve as a trapping region. I will show you Mathematica here in a second to close off this lecture A. Here are a few slides, let's just look at it this way, that go through the details that I showed you again in lecture 35A of how to construct a local Lyapunov function for the competing species model. I went through and typed up all the details. So here was the system, I did the Jacobian, I linearized, I did changes of variables like we've done with linear algebra a lot. I created a Lyapunov function for a diagonalized system. I converted on the next page that Lyapunov function to a Lyapunov function for the linearized system involving the Jacobian matrix, that's a J there. It's a quadratic form. Then I proposed a local Lyapunov function for the original nonlinear system. That was the competing species model near 0, 3, by essentially plugging in x and y minus 3 into this LJ function to get this thing, which is not a quadratic form because you have some first power terms and zeroth power terms. Here's the gradient vector for this local Lyapunov function. I take this derivative by taking the dot product of the gradient vector with the vector field. I haven't really talked about that, but that is one way to think about the chain rule. And you get this thing, which is not a quadratic form. In fact, it's got some cubic terms. And then I can show that that has a local minimum at the point 0, 3, and in fact even equals 0 there. Here I took the derivative along solution curves, that last function there, and differentiated it with respect to x and y, set those equal to 0 to find critical points. There is one at 0, 3, as well as 3 others. Something called the Hessian matrix allows you to get this matrix, which is negative definite, it turns out. This has negative eigenvalues, and that's what implies that this function is a local Lyapunov function. Yeah, lots of details there in 1 minute, but that's all we have time for because we need to finish this lecture A. I will show you one more thing in Mathematica here. Well, here's the system with the sine functions involved. Here, for example, is a trapping region, and you can see the solution curves going inside of it. They never go away. This essentially is defined by the local Lyapunov function in that example. And I do have Mathematica stuff about the other examples that I did here as well. But now I want to end lecture A. Thanks for watching.